And welcome back to the morning show. It's Wednesday, Wise Guys time. U of I physics professor Matt Sellon is back. In last hour, we ran a little LCD readout off a lemon.
Right. And I didn't quite explain how this works yet. I mean, basically, when you put copper and zinc together, electrons want to flow from the zinc to the copper, just because copper has a bigger affinity for electrons, but it can't because you don't have a circuit. So what you need is you have to have some place where the charges can flow in the other direction. And so what the electrolyte does, the acid inside the lemon in this case, is it basically provides, while electrons are flowing from the zinc to the copper on the outside through the wire, through the watch, whatever, positive ions are flowing from the zinc to the copper on the inside. Okay, and so everything can remain neutral that way, and you have a circuit, and basically the functioning of this acid in here, or it can in some cases also be a base, is that there's a chemical reaction between these electrodes and the liquid inside this lemon that provides not only the charges but also the energy for this thing to happen, because you have energy. You must have some kind of energy if you make a watch work or so on. So that comes from the chemical reaction. Now, this is not such a great battery because charges don't flow that easily through a lemon. So you can do the same sort of thing by just taking a film container, putting a little vinegar in it, which will take the place of the lemon juice, which was in the lemon, sticking a couple of nails in this thing through the lid. Okay, like that. Like this. Okay. And then when we hook this thing up to our voltmeter, we'll see, you can hang on to that so it doesn't fall over, okay? We'll see that we get about 0.9 volts in this thing, and also we get more current in this case. In this case, we get about a little over a milliamp. Okay.
So with the lemon, we had about the same voltage, but not as much current.
Right, we had the same voltage because the chemical reaction is about the same, but we had much less current. Now, what I've done here, since we want to be able to light up a little light bulb, is I've made 8 of these little vinegar-type battery things, and I wired them all up so it looks like a real evil contraption.
Yeah.
And by the way, if you ever want to test a battery to see if it's any good, you just kind of touch your tongue to it.
Yeah, I do it all the time.
So here you can actually, I won't make you do it because I licked it now.
But like 9 volts?
Yeah.
You got to
get a great joy
I love
the 9
doing
volt. So this, now we have, basically we have one set of 4 little vinegar batteries here in parallel with one set of 4 right here. So when we hook this thing up, we should get about 4 volts, and we should get about 4 milliamps of current, which is enough to make this LED light up kind of brightly. I'll show you first.
Hey,
I'll show you right there. Okay, so if you can, it may be a little hard to tell on TV, but anyway, it is lighting up.
It is.
And so you can actually now, you can run stuff from this. Now, people don't make batteries like this because, well, you know, they spill and you get vinegar all over the place and it's icky. Believe it or not, though, the chemical reactions and the science behind these batteries are exactly the same as what you get in these little tiny hearing aid batteries or your D-cell batteries. Usually each element in a battery is about 1.5 volts. Because of the choice of the metals in the electrolyte. And if you look inside a 9-volt battery, you basically have 6 little tiny batteries.
Very good. Awesome. Now we can run stuff at home and do our own experiments.
And I think we're going to make an electric pickle next week.
Electric pickle. Can't wait for that. Matt Sellon, U of I physics professor. He's the wise guy. He'll be back next week making an electric pickle. There you go. There's the website. We'll be back with more of the morning show right after this.